Hello, am I audible? Okay. You can mute yourself. Okay. So my name is Saleh Khan. I'm a PhD student at IIT Delhi, and I will be conducting these problem-solving sessions for the NPTEL course Advanced Power Electronics and Control, which is taught by Professor Avik Bhattacharya from IIT Roorkee. So in these power problem-solving sessions, basically we will be having every Monday from 6 to 8 p.m. and we will be covering the some of the problems related to the weekly course content that you have been taught. So these will not be the assignment problems of that week, but later on, after the coming from the second week, we will be covering the assignment problems of the previous week after the submission deadline is over. So in each week, we'll basically I'll provide a summary of the content that has been taught, and then we'll uh, go on solving some problems. So you can ask any questions in the meantime. Whenever you want, you can ask them in the chat, or you can raise your hand and I'll call you and you can ask over the microphone. And we'll also have some 5 minute break after 1 hour or so. So let's begin. Okay, so starting from the summary of the first week contents that have been taught. So in this week, the course content that was taught was included some introduction to power electronics and the applications of power electronics, the advantages of power electronics. It also talked about some basic concepts of switches, how power electronic converters work, and how they work in different applications, and what kind of different switches are available and what are their features. And then the course went into the device physics of different switches. So, coming to the introduction, oh, what was mainly taught was the application of power electronics and what is the reason we use power electronics. So, power electronics basically involves converters and control applications where we can change the voltage level from one level to another, or current level from one level to another, or frequencies. So that means that we can change one DC voltage to another DC voltage, or we can change one DC current to another DC current. Similarly, we can convert a DC voltage into an AC voltage, a single phase AC voltage or a three phase AC voltage with varying frequencies as well as varying amplitudes. And also we can convert it vice versa, so from AC to DC. So all four types of conversions are possible from DC to DC, from DC to AC, AC to DC, and AC to AC, from one AC frequency to another or one AC amplitude to another. And what is important in power electronics is not only we are able to do this conversion very flexibly and with very high level of control, but we are also able to do it with high power conversion efficiency. As we'll see later on, other methods of power conversion, they involve a lot of losses, power losses. So in power electronics, we are able to achieve over 90% of efficiency over the entire power level and uh, the different voltages that we require. So why do we need power electronics? So if we have a supply coming to our homes or generated by in power plants, why do we need power electronics? So first of all, because we need electricity at different voltages and at different power levels. And because of that, a DC transformer does not exist. So we are able to convert power from one AC level to another AC level using a transformer, but it only works for AC power and it only works for one particular frequency. Uh, do you want to ask a question? Okay, you can mute yourself and you can lower your hand. Okay, so as I was saying that in AC power we are able to convert from one voltage to another, as so, and conversely we will be able to convert from one current level to another, but we cannot convert one frequency to another. And as we will see, uh, the frequency variation is needed in some cases. But more importantly, we cannot convert from AC to DC at different power levels using a transformer. So that is why we require or we make use of power electronic converters to convert DC power from one voltage level to another voltage level. And transformer does not give us a lot of control. For example, if we have a transformer with say let's say 1:10 turns, and we have a voltage of 100 volts on the primary, the secondary voltage will give us 1000 volts only. So because we cannot change the number of turns, then physically change the number of turns while the transformer is in operation. So it does not allow us control and flexibility. But as you will see, power electronic converters, they provide us with this ability to change the power level while in operation to whatever desired level we want. And also, more importantly, we are able to achieve high power density using power electronics. So what does the high power density means? So by achieving high efficiency, we are able to reduce the losses that are happening during the conversion process. And if the losses are minimized, then we can reduce the size of the converter. So how is losses related to the size? Because while we want to conserve energy, that is a good initiative, but that is not the only reason we want to have high efficiency. Because when we have low efficiency, then power is lost as heat. And if we have a very small area where power is being lost, then that area will heat up. And if it heats up to a high level, then that converter, that object, or that component will get damaged. So if we are able to achieve high efficiency, then we can make the size of that component as smaller and smaller so that it will not heat up as much because of the high efficiency. And that means we are able to get high power devices in a very small compact form. So like in your phones, in your laptops, in your chargers, we make use of power electronics, and as power electronics improves, the size of these objects also reduces. So that is one of the main advantages of power electronics. Now, power electronics has applications in a wide areas. So, for example, one of the main applications right now is in renewable energy integration. So, using solar panels and solar energy, we are able to produce DC voltages, and these voltages are fluctuating, the current and power levels are fluctuating, but we are able to connect these DC voltages to the our AC grid using power electronics as an interface, that we're able to convert from the DC voltage to the desired AC voltage of the grid. And similarly with wind we are able to generate DC or as well as AC power, but the AC power may not be at the same frequency as the grid power, or it may have different amplitude because the wind speed can change. So using power electronics, we are able to integrate these renewable energy sources with our grid, which is at 50 hertz and a particular frequency as well as a particular voltage. Also, using power electronics, we are able to achieve variable frequency motor drives. So these motors, AC motors, are able to we these AC motors run basically at different frequencies, and depending on the frequency, the speed changes. For if we require high speed, we want the AC waveform to have high frequency. And using the conventional, if we have a supply 50 hertz supply, we cannot change the frequency of that supply. So that is where we use power electronics to change the frequency as well as the voltage level to achieve precise control of the speed as well as the torque of the motors. And this has applications in machines, in vehicles, in robotics, in a lot of different areas where motors are used. Another application which is very important these days is electric vehicles. So in electric vehicles, we have a DC battery and a three-phase AC motor usually in light motor vehicles. And to convert from this DC power to three-phase AC power, we make use of power electronic converters. as well as to charge the DC battery from the grid, from our power supply at our homes. We make use of power electronic converters to convert that AC power to DC power. So also we make use of power electronics in power supplies, such as uninterrupted power supplies that you have at your homes and schools and colleges, where you again you have a battery bank, and then you have an inverter which uh, inverts this DC battery voltage to AC voltage that uh, then you can use at your homes and uh, other places. So it can we can have DC AC to DC power conversion, AC DC power conversion, like I mentioned, using UPS and inverters. You can also have DC DC power conversion. So because various electronic devices they require voltage DC voltages, but at a very small level, at maybe 10 volts or 20 volts. So from the AC to from the using the inverter or rectifier, if we have get a DC voltage, then we can transform this DC level to another DC level using DC-DC converters. So also, because we don't have DC transformers, we were not able to achieve DC transmission uh, for a long time. But after the coming of power electronics, now we can basically, using power electronics, we can convert from AC or a low voltage DC to a high voltage DC level. And then we can transmit this DC power over long distances without much losses. So this is called high voltage DC transmission, or HVDC. And this has been made possible with the use of power electronics. Lastly, the one of the other main areas of power electronics is power quality. So we want to have high power factor so that we don't so that the losses in our transmission lines, as well as the apparent power that we get, is minimized, so that our converter sizes are also reduced. The size of the converters and the electronics is reduced. So that is basically called power factor correction, because many appliances that we use, or in fact the power electronics itself that we use, it leads to low power factor. And when we have low power factor, to achieve a given active power, we will require a higher level of total apparent power. And that means we will have higher currents that will lead to more losses, more I square R losses, as well as the rating of the wires as well as the devices will be higher. So high power factor, or power factor close to unity, is desirable. So that is so using power electronic converters, we are able to achieve high power factor, as well as reduce the harmonics in our line. So we'll study the effect of harmonics later in the course. So now coming to how exactly power electronics works. And so this is a very popular example to say show that, for example, if we want to convert DC voltage from 100 volts to 50 volts across a 10 ohm load. So one way to do it without power electronics is using a resistor divider circuit, as you can see in this slide. So if we want 50 ohms, 50 volts at our load, and when the load is 10 ohms, we can make use of another 10 ohm resistor, and we can connect it in series with our load. So as you can see, using a voltage divider concept, the 50 volts will be dropped across the first 10 ohm resistor, and then we will achieve 50 volts across our load. But in this way, we are only able to achieve 50% of the power that is supplied to the load, while 50% is being lost in the other resistor. So that means our power conversion efficiency is only 50%. So for example, in this case, if our 100 volt source, it supplies a given power, only 50% is reached to the load. So the other 50% is lost in the resistor. So not only is it very inefficient for very high power applications, this will mean that the other resistor will have to be a very large size, because to, for example, if we have 1 megawatt system, that means 500 kilowatt will be lost. So 500 kilowatt in a resistor, that will be a huge amount of power loss that will require a very large heat sink, very large fans to dissipate this power. Otherwise, the resistor will just burn. So how does power electronics solve this problem? So now power electronics, if we want to have the same objective, using from a 100 volt DC source, we want to achieve a 50 volt across our 10 ohm resistor, we can make use of a switch in series with the source, that 100-volt source, and the 10 ohm load. So to achieve 50 volts at the output, which is 50% of our input 100-volt source, we can turn on this switch for 50% of the time and then turn it off for 50% of the time. So when this switch is turned on, the entire 100-volt will come across our load, as you can see in this graph. And when this switch is turned off, that means the load is disconnected from the source. So the voltage across the load will be zero. So if we are able to do this periodically, after every t interval, capital T, if we are able to turn this switch on and off, and that on time of the switch is basically T by 2, which is 50% of our period, then on an average, we will be able to achieve 50 volts across our load. And this averaging is done using filters, using inductive and capacitive filters. So in this way, we are able to achieve uh, the desired 50 volts at the load without uh, without that 50% loss. So as we can see, if we have a very ideal switch that can turn on and turn off instantly, and it does not have a forward voltage drop and it does not have a leakage current, then we can achieve very high efficiency of this power conversion. And also the switching frequency of this switch. So the reciprocal of this time t period, this is called the switching frequency of the switch. And if we have a very high switching frequency, that means our output voltage will have an average value of 50 volts plus a very high frequency AC voltage. And if we have a high frequency AC voltage, we can use a smaller value of filter to uh, attenuate this high frequency. So, so in order to reduce the size of the filters, we can increase our switching frequency. But as we'll see, that switching frequency in a practical switch comes at a cost. So this is the basic concept of power electronics. So here we took an example of a DC-DC conversion. But now if this switching that we are doing, if we can, so instead of a constant 50% duty ratio basically is the time that switch is on divided by the entire time of the switching period. So right now we are in this example, we have a 50% switching ratio, duty ratio, because the switch is on for T by 2 and the switching period is of T seconds. So in this way, we are able to achieve 50% of the input voltage at the output. But if we are able to change this duty ratio, then the average value of the output voltage will also change. And so in that way, we will able to achieve different voltages. So not only at 50 volts, but at higher voltage or lower voltage. But not only DC voltage, if we can change this duty ratio in a sinusoidal fashion, at the output, we will get a sinusoidal voltage, which is the concept of AC to DC converters, as we will see later on in the course. So this is the basic concept of power electronics. Now, this switch that we are using, uh, it should have some ideal features that we want. So one of the ideal features is when the switch is off, it should not allow any current to pass through. So the off or open state current should be zero. So this is called the leakage current. In a practical switch, this will not be zero. There will be some leakage current, and depending on the switch, it can be significant or it can be insignificant that we can ignore it. The second thing that we want in an ideal switch is that when the switch is turned on, the voltage drop across that switch should be zero. But again, practically, we will not be able to achieve this zero voltage drop switch. So as you know, in a diode, we get a voltage drop of 0.7 volts in a normal diode, but in the power diode, this voltage drop will be different. But nonetheless, we get some voltage drop. So in every switch, practical switch that we have, we will get some voltage drop. And that voltage drop will lead to some power loss in the switch during the turn on time, because the switch will be carrying some current. And if it has a voltage drop, then that voltage drop times that current will be the power loss in that switch. So lastly, the third feature of an ideal switch is that the transition between the on state to off state and from off state to on state should be instantaneous. That means that we want that switch to turn on at with zero transition time, because for example, when the switch is in off state, it is blocking the entire voltage, and when the switch is in on stage, it will carry the entire current. So during the switching interval, if this interval is not instantaneous, then the switching voltage will drop slowly and the switching current will rise slowly. And during that time, when the switching voltage and the currents are not zero, there will be some power loss in the device, and that is called the switching loss. So in order to avoid these losses, the conduction losses and the switching losses, we want to achieve as well as close as possible to the ideal switch. But in reality, we will not be able to achieve this ideal switch. So one of the ways that we can use a switch is a mechanical switch, where we can have physical contacts, metallic contacts, and if we connect these physical metallic contacts, then the switch is on. If we disconnect them, then the switch is off. But this connection and disconnection is very slow in mechanical switches. That is why we make use of electronic switches, which are made of semiconductor devices, where this turn on and turn off takes place in the micro or nanosecond time duration. So now we will see some of the available devices that we can use in different converters. So one of the basic switches that we have is a diode. So on the left, you can see the diode, the symbol of the diode. And on the right of this symbol, you can see the a VI graph. So this graph basically shows the area of operation of this diode. So when we apply a positive voltage across this diode, which is greater than the knee voltage or the barrier voltage, then this diode is able to conduct positive current. So that means the positive current area has been highlighted, but it does not block any positive voltage. Any positive voltage that is greater than the barrier voltage, it will just turn the diode on. But the diode is able to block a negative voltage. So if we apply a negative voltage across this diode, that means at this positive terminal, if we apply a negative voltage with respect to the negative terminal of the diode, then the diode will block that voltage up to a certain breakdown voltage. So that means the diode, the operation of the diode is a single quadrant switch. So as you can see, it allows positive current and it blocks negative voltage. So that makes it a single quadrant switch in the second quadrant. And as you will see, and you have studied in the course content, that the diode is an uncontrolled device. So it only has these two terminals and we cannot control the turn on and turn off. The turn on and turn off is decided by the circuit and the circuit currents and the circuit parameters. So now on the right side, you can see a different kind of switch, which is a silicon control rectifier or a thyristor. In short, we can call it an SCR. So this device has three terminals. Apart from the anode and cathode, it also has a gate terminal. And that allows it basically to block forward voltage as well. So by applying a positive voltage, which is even greater than the barrier voltage, this device will not allow any current to go through this device unless and until we provide a current through the gate terminal. So that means it will block positive voltage and it will also block negative voltage, just like a diode. But when we pass a current, positive current through the gate terminal, then it will turn on and allow positive current to go through it. So this is a two-quadrant device. The first and the second quadrant we are able to achieve from this. Yes. Okay. So SCR. So this, I'm not going into the device physics. I'm just talking about the the resulting operation of the SCR. So it has three terminals. The positive terminal here, which is the anode, the negative terminal, which is shown here, is the cathode, and it also has a third terminal, which is the gate terminal. So the diode was not able to block any positive voltage, but the SCR, if we apply a positive voltage and we do not uh, give any voltage or a current to the gate terminal, then the SCR will block that positive voltage. So that means if we have a voltage across the positive and negative terminals of the SCR, it will not allow any current to pass through unless and until we provide a current through the gate terminal. So once we provide a current to the gate terminal, which has to be of some value, then the device physics works as such that the SCR will turn on. So the voltage across this will drop and the current through it will rise. And it will basically go in this region of operation. So depending on the circuit parameters, what the circuit current that uh, is applied to the SCR, it will turn on and it will carry that current. But again, the SCR is it can be controlled to turn on, but it cannot be turned off. It will only turn off based on the circuit parameters. And whenever the circuit voltage becomes negative or the current becomes negative, only then it will turn on. So this is the diode and SCR. So any questions about this? Okay. So the next group of switches that we have are transistors. So on the left, you can see two transistors. The leftmost is the BJT, and on the right of the BJT is an IGBT. So these two devices, so they are also three-terminal devices. So they have a collector, emitter, and a base, or in case of the IGBT, it has a gate terminal. Uh, Now, but the advantage of using BJTs and IGBTs is that we can have both controlled turn on as well as turn off. So in case of the BJT, when it will block positive voltage unless we provide a current through the base terminal. So once we provide a current through the base terminal, then it will turn on and it will pass positive current through the BJT. And when we remove this base current, it will again turn off. So based on the base current, we are able to turn this BJT on and off. Similarly, the IGBT, based on the gate source voltage, so in the gate or gate emitter voltage, based on this voltage, we are able to turn the IGBT on and off. Again, it will block positive voltage and it will conduct positive current. But BJT and IGBT, they are not able to conduct in the negative direction, as well as they are not able to block negative voltage. So these are all also first one quadrant devices, but they are in the first quadrant compared to the uh, diode, which is also a one quadrant device, single quadrant device, but it is from the second quadrant. The MOSFET, on the other hand, it is able to allow current to pass through in the positive direction as well as in the negative direction. That is from the negative terminal to the positive terminal. So once once we supply the gate voltage to the MOSFET, then it will turn on, and depending on the whatever the circuit parameters are, it will allow positive as well as negative current to pass through. But it will only block positive voltage. It cannot block negative voltage. If we apply a negative voltage, it will just uh, it will just turn on in the negative direction because it has a body diode from the negative to positive terminal. So these are some of the devices that we are able that are available to us for use, their uh, and their characteristics in the VI graph. So in the course this week, you were taught the device physics of the SCR, the diode, as well as the GTO. So I will not go into the details right now. I will just give some general concepts of the device physics that will help us determining how uh, the voltages and the resistances and the switching speeds are determined. So in all the devices that you will study, there will be a PN junction in these devices for semiconductor PN junction. And the breakdown voltage of this PN junction is a function of the doping level of the different P junctions, the P substrate as well as the N substrate. So if we want to have a high breakdown voltage, that means we want to have the rating of the device should be high. One way to achieve this is to have a low doping in the semiconductor. So doping is the amount of impurities that we have in the semiconductor by using, so if the doping element has more electrons, then we call it N-type doping, and if it has less electrons than the basic semiconductor substrate, then we call it P-type doping. So, but the point here is the concentration of doping will determine the breakdown level of the device. So, to have a high breakdown level, we can have a low doping concentration. But this low doping concentration will result in high resistivity. So that means when the device will turn on, the resistance of that device will be higher. So for example, if we have a 100-volt diode and a 200-volt diode, the basically the on drop of the diode for the same current level will be higher in the 200-volt diode because it has basically high voltage rating. So, so that means the higher voltage rating comes at a cost of higher resistance. So now we can have different types of uh, uh, semiconductor devices. So one of the semiconductor devices is called majority carrier devices. For example, MOSFET and Schottky diodes, these are majority carrier devices. So that means that, for example, if we have a P-type semiconductor, a semiconductor which has been doped with a P-type semiconductor, so that means the number of holes is more. Yes, Mohana, you have a question? So if anyone has a question, you can write in the chat. So yes, this so someone is asking whether this material will be downloadable. Yes, the lecture is being recorded, so it will be available on YouTube, and the slides will be provided to you. So doping. So basically, in all the devices that we are using, these are basically semiconductor devices. So semiconductor devices like silicon and other gallium or silicon carbide, whatever these devices that we are using, they have they use covalent bonds, and all of the basically electrons are connected to other atoms. But if we are able to introduce some impurities in the semiconductor with atoms, with elements which have more or less number of electrons, that is called doping. So if we introduce uh, elements in the semiconductor which has more number of electrons than the basic semiconductor substrate, that is called N-type doping. So it has more number of electrons, so it is negatively charged. So it is not negatively charged, but it has more number of electrons. Yes, so you will be able to, you will, in the voltage YouTube links will be sent to you. So if they're not sent to you, then in the next class, on the next Monday session, I will basically send you the YouTube links. So this was so doping is basically adding impurities to the semiconductor to get more electrons or more holes, and that these holes or electrons are used then in the conduction process. So majority carrier devices, for example, in N-type device, in an N-type semiconductor, the electrons are the majority carriers and the holes are the minority carriers. Similarly, in a P-type semiconductor, the holes are the majority carriers and the electrons are the minority carriers. So depending on the device, different device, they use different carriers. For example, MOSFET and Schottky diodes, they use majority carriers to have the conduction process. And in the majority carrier devices, the on resistance will increase with the rated voltage, as I have explained. But in a minority carrier devices like diodes and SCR, BJT, and IGBT, they have a phenomenon that is called conductivity modulation. So using this conductivity modulation, what happens is that the minority carriers are injected into this lightly doped region. So because of the presence of these minority carriers in the lightly doped region, the on resistance of the device is reduced. However, this reduction in the on resistor comes at a disadvantage. The disadvantage is that the switching speed of the device is reduced. So that means that turning on and turning off of this minority carrier devices is slower compared to majority carrier devices. Because this injected minority charge, it is difficult to introduce it into the lightly doped region as well as to remove it from the lightly doped region. So this leads to more time. More time takes to remove this minority charge, so that reduces the switching speed of the device. And if the switching speed is reduced, that means the switching losses will be high. So basically, what I'm trying to say here is that majority carriers have an advantage that they uh, they will be able to switch at a higher speed. So that means we can use them at higher switching frequencies. However, the on resistance of majority carrier devices will be high with high rating of voltage. But minority carrier devices, on the other hand, have the opposite feature. So their on resistance will be less due to this presence of minority carriers, but the switching speed of the minority carrier devices will be low. So we will not be able to use them in high switching frequency applications. So this was a summary of the general concepts of the device physics. So now we will come to the problems, some sample problems that are related to the contents that have been taught in this week. And in during the course of these problems, we will also come into some of the detailed device physics of different devices. So the first problem, so I will ask you to basically, so these are very simple questions for the first couple of weeks. So I will ask you to provide what you think are the answers in the chat. So, for example, the first question is MOSFET is which type of device? And the options are current control current device, current control voltage device, or voltage control voltage device, or lastly, voltage control current device. So these are the four options. So you can type in the chat A, B, C, D what you think is the answer, and then we will discuss the answer. Okay, so some have got the answer correctly. It will be voltage control current device, and we'll see how it works basically. So the MOSFET is shown on the left side. So again, it has three terminals. The positive side terminal is drain. The negative side terminal is source, and then we have a gate terminal. So in a MOSFET, the current through the gate drain is a function of the VGS voltage. So the gate voltage with respect to the source is called the VGS voltage. So once this gate to source voltage, once it crosses a certain threshold voltage, then the device will conduct. And the current through the device, that is the drain current, is a function of the VGS voltage. So as the voltage crosses the threshold voltage, the MOSFET will start conducting. And as the VGS voltage increases, the current conduction through the device, through the MOSFET will increase. So basically, the MOSFET is basically a voltage control device. That means depending on the gate to source voltage, we can turn it on and turn it off. So once the gate source voltage increases more than the threshold voltage, it will turn on. And once it decreases less than the threshold voltage, it will turn off. And turning on and turning off of this switch is basically how much current it allows to pass through. So it is a voltage controlled current device. So compare this to the BJT, which is shown on the right. So again, it also is a three-terminal device, as I mentioned. It has a collector, emitter, and a base. So, but here the collector current is a function of the base current. So that means if the base current increases, only then the collector current will increase. So that means it is a current controlled current device. So the collector current will only flow after the base current is supplied. So that means the answer to the first question is basically D. The MOSFET is a voltage controlled current device. Okay, so that was the first problem. Now the second problem is, as compared to PN junction diodes, what are the features of Schottky diodes? So the options basically are about the operating frequency as well as the reverse leakage current. So you can give your what you think is the answer, whether the Schottky diodes have low frequency, high frequency, low reverse leakage current, or high reverse leakage current. So you can guess your answers. Okay, so most of you are saying B, which is high operating frequency and low reverse leakage current. Okay, now we'll come to the answer. So now first we'll to compare the Schottky diode to a normal diode. We'll first talk about the normal PN junction diode. So the PN junction diode basically has two semiconductor regions, or three in this case for the power PN junction diode. The first region is doped with a P semiconductor, and the other region is an N semiconductor. So the N minus is basically the lightly doped region. So in a PN junction diode, what happens is that when we apply a positive voltage across the anode, when we apply a positive voltage across the anode, uh, the holes from the P terminals are injected into the N region. So the holes in the N region, the holes are the minority carriers. So that means the PN junction diode is a minority carrier device. And when we want to turn off the PN junction diode, we need to remove these holes from the N region. So that happens by uh, a reverse current that flows from the cathode to the anode. So that is called a reverse recovery current. And the charge that we have to that is stored in the N region is called reverse recovery charge. So basically, in a PN junction diode, during the turn off process, what happens is that the current becomes negative, and this negative current basically removes the holes from the N minus region. And only after this minority charge has been reduced is the PN junction diode able to turn off. So that means it takes a certain amount of time, which is called a reverse recovery time, to turn off the PN junction diode. So that means the PN junction has a slow switching time. So we cannot use it for high switching frequencies. Now compare this to the Schottky diode. In a Schottky diode, we do not have a PN junction. It has a metal semiconductor junction. So that means the anode side is connected to a metallic portion. It is not connected to a semiconductor. And then the metal is connected to an N-type semiconductor. So in this case, the carriers are electrons from the metal. So, and these electrons are the majority carriers in the N-type. So that means we do not have any minority carriers, and we do not require any reverse recovery current or reverse recovery time. So that means we are able to achieve faster switching. So we can use high switching frequencies. However, because we don't have a PN junction, in this case, what happens is that the depletion region is smaller. So so in the for reverse blocking, since the depletion region is smaller, the electrons and holes are able to cross this depletion region readily compared to the normal p-n junction diode. So that means the Schottky diode has a higher reverse recovery leakage current. So basically, what happens in a Schottky diode is that the faster switching comes at a cost, and the cost is that the reverse leakage current is higher compared to the p-n junction diode, as well as the voltage ratings of the p-n junction are uh, lower compared to the normal semi p-n junction. So sorry, the voltage rating of the Schottky diode are lower compared to the p-n junction. So if someone's mic is turned on, so can they please mute themselves? Uh, Hema, I think Hema. Okay, thanks. So now basically the answer to this question is the PH Schottky diodes have a higher operating frequency because they don't have reverse recovery uh, phenomenon, but they also have a higher reverse leakage because of the lack of p-n junction. The depletion region is smaller, so the in for reverse blocking, the electrons and holes are able to cross over this smaller barrier potential very easily. So the Schottky diodes have a higher operating frequency and a higher reverse leakage current as well. So this was the second question. Now we can come to the third question, which is what is the difference between a diode and a triac? So you can give your suggestions, what you think is the solution to this question. So the option is that diode has a control turn on and the triac has a control turn on. Or it can have a control turn off, or whether they need a gate pulse, or whether it is about unidirectional current flow or bidirectional current flow. Okay, so most of you have guessed this correctly. Uh, so Mohana has raised her hand. So do you have a question? And Sangeeta? Okay, I'll just carry on. So again, the diode is basically a simple PN junction. It is uncontrolled. So there is uncontrolled turn on and turn off. Uh, Whenever we apply a positive voltage, it will just turn on beyond the barrier voltage, and when the voltage becomes negative or the current becomes negative, it will turn off. But the current can only flow from anode to cathode, so it has a unidirectional current flow. The triac, it stands for triode for alternating current. The structure of the triode is shown here. It is basically equivalent to two SCRs connected in reverse parallel. So one SCR is connected from T1 to T2, and another SCR is connected from T2 to T1 in the reverse direction. And the gate terminals of both these SCRs are the same. So that means when we apply a gate current, the triac will turn on. And since we have both directions, it can conduct from T1 to T2 as well as from T2 to T1. So it has bidirectional current flow, but again, it only has control turn on. It does not have control turn off, just like the SCR. So based on these features uh, and the options that we have, so the first option is wrong because the diode does not have controlled turn on, even though the triac has controlled turn on. And the second option is also wrong because the diode is basically uncontrolled. It does not have control turn on and control turn off. The third option is wrong because the diode does not have a gate pulse, and the triac does need a gate pulse. So only the last option, which says that the diode has unidirectional current flow from anode to cathode, and the triac has bidirectional current flow. So from both terminals, the current can pass through. So the last option, which is correct. So the fourth problem is AC motor behaves like which type of filter? So your options are low pass filters, high pass filter, band pass filter. So you can give your suggestions what you think is the answer. Okay. So most of you have guessed correctly. So so here you can see on the left is a typical three-phase AC motor. So AC motors can be single phase or three phase. So motors usually have a rotor and a stator. And three-phase motors, we have stator windings on the stator. And these windings are basically uh, coils with an n number of turns, and they are distributed along the stator structure. And these are inductive windings, and whenever current passes through these windings, a magnetic field is produced. The rotor can have windings. So for induction motors, the rotor can have windings or it can have squirrel cage. For synchronous motors, it can have a magnet, an electromagnet, or a permanent magnet. So whatever the case, the stator basically has inductive windings. So we can represent these inductive windings using inductances, which are shown on the right side. So this is a star connected inductive three-phase winding. So, and as you know, the in an inductor, the impedance of an inductor is omega times L, where omega is the angular frequency 2 pi f and L is the inductance. So the current through an inductor will be the voltage through that inductor divided by the impedance. So that means if the frequency of the voltage is high, then the impedance that is provided by the inductive winding will also be high. So that means the inductive windings will behave as a low pass filter, because for DC as well as low frequency AC, they will allow or not attenuate the low frequencies much compared to the high frequencies. So that means the AC motors behave as low pass filters. And this has some advantages for power electronics as well. So, for example, in a power electronic converter based motor drive, what we have a supply which can be a single phase supply or a DC supply or a three phase supply. And then we have a power electronic converter which is connected to the AC motor. And so, as I showed before in the example of the DC to DC conversion from 100 volt to 50 volts, the output voltage that is produced by the converter has square waves. So, for example, VA I have shown here, it is basically square wave. Sometimes it is positive voltage, sometimes it is zero. And the width of this positive voltage can also change using the power electronic converter. And using the power electronic converter, this voltage can also become negative. So as you can see, the voltage VA, it has a low frequency fundamental, which varies sinusoidally. So basically, what that means is initially the width of the voltage is less, and then the width increases, and then it again becomes less, just like a sinusoid. And then the voltage becomes negative. And again, the negative voltage width first is small, and then it increases, and then again it becomes small. So it has a low frequency fundamental as well as a high frequency. The square wave is basically at a very high frequency. And because the AC motor is a low pass filter, it acts as a low pass filter because it has inductive windings. It will attenuate the high frequency component and it will pass the low frequency or the fundamental component. So that means by using this power electronic converter, we are able to achieve a sinusoidal current or a sinusoidal current with some harmonic component uh, in a very efficient manner. Because as I showed before, the power electronic converter does not have a lot of losses compared to a resistive divider. And using this power electronic converter, we can not only vary the amplitude of the resulting sinusoid fundamental, we can also vary the frequency. So these are the advantages of using a power electronic based converter drive. So the answer to the fourth problem was a low pass filter. The AC motor behaves like a low pass filter. Now the fifth question is a variable frequency drive is used to, and the four options are the controlling motor speed and torque by varying the motor input voltage, or the we can control the speed and torque by varying frequency as well as voltage, or we control the motor input frequency and voltage by varying speed and torque, or the last one is that we can control the motor current and voltage by varying speed and torque. So does someone have any question? Harshita, your mic is on. Do you have a question? Okay. Okay, now has it changed? Okay. So basically, the fifth question is in a variable frequency drive, what is the function of the variable frequency drive? And the options are whether we can control the speed and torque by varying the input voltage, or we can control the speed and torque by varying the frequency as well as voltage, or whether we are controlling the frequency and voltage by varying the speed. So you can Rainil is asking the function of an inductor depends on its arrangement also, right? Yes. So depending on the machine, the inductor windings are arranged in a particular fashion. But the overall concept is that the windings are inductive because they have to produce a magnetic field. So they will have an inductance, a magnetizing inductance. And whatever the inductance value, it will depend on the machine rating, machine configuration, the arrangement in space, and the mutual inductance with the rotor. And so whatever the case, uh, it will have an inductive feature. So that will lead to a uh, low pass filtering properties. So, okay, so coming to the variable frequency drive. So some of you have guessed the answer. So now here I am showing one example of a variable frequency drive in more detail. So this one, we have a three-phase supply, which can be a 50 hertz or, okay, so yes, Renil is asking whether the motor can act as low pass filter as well as high pass filter depending on the series parallel arrangement. Yes, but the motor drives are usually not connected in series or parallel. So they don't have high capacitive elements. We can parallel them, but the paralleling will only uh, decrease the inductance, but they will not add a high pass filtering effect. So the AC motor will always have a low pass effect. But if we add different capacitors or some other components, then we can get a high pass filtering, but that will not happen in a AC motor. Okay. So here I'm showing a power electronic converter based variable frequency drive. The supply is a three-phase AC supply, and this supply will have constant voltage like 415 volts or some other voltage and constant frequency, 50 hertz or 60 hertz. But for the AC motor, if we want to control the speed of the motor, we will need to control the frequency of the supply because the AC motor speed will depend on the frequency of the supply that is given to the AC motor. By increasing the frequency, the speed will increase, and by decreasing the frequency, the speed will decrease. But if we want to keep the magnetic flux in the AC motor constant, we will have to keep the V by F value constant. So what is the V by F? V by F stands for voltage divided by frequency. So the supply voltage divided by these supply frequency to the AC motor has to be kept constant in order to produce the rated flux. So as the speed changes, the frequency will change. And if we want to increase the speed, we will have to increase the frequency. And that means to keep the V by F ratio constant, we will also have to increase the voltage. And this cannot be done by the fixed three-phase AC supply that we get. So that is why we make use of a power electronic converter. So here on the left side of this power electronic converter are these six diodes. So this is a three-phase rectifier. So what this will do, it's basically convert the three-phase AC to a DC voltage in an uncontrolled fashion. So it will not control the level of the output voltage, and this capacitor will basically keep basically filter out the voltage level and give us a constant voltage at the DC link. And for example, if the AC voltage is 415 volt RMS, that means the peak of the voltage will be around 560 volts. So around that voltage we will get at the DC link. And then we have a voltage source inverter. Suruchi, do you have a question? If you don't have a question, you can please turn off your mic. Okay, let me just mute. Okay, so on the right, you can see a voltage source inverter which has six IGBTs in this case, and IGBT with a diode connected in the anti-parallel fashion. So using this converter, which is on the right side, it is called a voltage source inverter. Using this voltage source inverter, we can achieve variable voltage and frequency for the AC motor supply. And so basically using this power electronic converter, which is a variable frequency drive, we are able to achieve variable frequency and variable voltage amplitude. In that way, we are able to control the speed as well as the flux of the AC motor. And the torque of the machine can also be controlled separately using a more complicated method called field-oriented control, which is a separate subject which can be studied in uh, power electronic drives. So basically, the answer to this question is that we can control the motor speed as well as torque by varying the input frequency as well as the voltage. Okay. So the next question is, which of the following has bipolar voltage withstand capability? So the options are SCR, GTO, SCR, GTO both, or none. So you can give your guesses in the chat. Okay, some are saying D and some are saying C. Okay, so the uh, structure of the SCR and GTO is shown on the left and right respectively. The SCR has three terminals, the anode, which is A, the cathode K, and which is, so these two Ks are connected together outside, and the gate terminal. So the GTO is basically a similar to SCR. So coming to the SCR, it has a one P layer connected to the anode. Then we have an N layer, then another P layer which is connected to a gate, and then another N layer. So it basically has three junctions, J1, J2, and J3. The GTO, which is a gate turn-off thyristor or a gate turn-off SCR, it also has the same overall structure. So it also has a PN structure, but the terminals are connected differently. So it will have multiple uh, gate as well as cathode terminals. But the point here is for both SCR and GTO, depending on the polarity of applied voltage, one of the PN junctions is reverse biased. For example, if we apply a positive voltage to the anode compared to the cathode, then the J1 junction, this junction, J1 junction will be forward biased. The J3 junction, which will also be forward biased from P to N, but the J2 junction will be reverse biased because the J2 junction from A to K going into the A to K direction, it there first is an N layer and then there is a P layer. So the J2 junction will be reverse biased when we apply a positive voltage to the anode. Similarly, it will happen for the GTO because it also has the same junctions J1, J2, J3. So basically, the SCR will block positive voltage. So if we don't have any gate current, it will block positive voltage due to the J2 junction. Similar is the case with GTO as well. Now, if we apply a negative voltage to the SCR or GTO, for example, if the K terminal now is positive, then the J2 junction in this case will become forward biased, right? So the P and N minus J2 junction will become forward biased. But the other two junctions, the J1 and J3 junctions, will be reverse biased. So again, it will block negative voltage. So SCR and JTO, they are both able to block positive as well as negative voltages, right? So that means that they have bidirectional uh, voltage blocking capability, but they are only able to allow current from anode to cathode. So when we give a current to the gate from gate to cathode, so it will uh, create charges that will basically turn on the GTO, the SCR. Similarly, with GTO, when we pass a current from gate terminal, the GTO will turn on, but the SCR we will not be able to turn off. But the GTO, in case of the GTO, we are able to turn off the GTO using a negative gate current. So that is the difference between SCR and GTO. But the common thing in both cases is that they are able to block both positive as well as negative voltages because of the different PN junctions. So in both cases, the positive as well as the negative voltages, one of the PN junction is reverse bias. So that allows the SCR as well as the GTO to block positive as well as negative voltages. So the answer is SCR and GTO both are able to withstand bipolar voltages. Okay. So before carrying on, we will just take a short 5 minute break. So we will begin at 7:20 then, a 7 minute break. So you can just take a break, short break, then we can continue for the rest of the problems. Okay. Okay, so we can continue now. Am I audible? Okay, so the seventh question is, what is the relation between the breakdown voltage and the drift region of a power diode? So you can uh, post your guesses. So whether it is the relation between the breakdown voltage in the drift region is directly proportional, inversely proportional, or it cannot be both, but it can be D. So whatever you think is the answer, you can type in the chat. Okay, so so again the power diode is shown on the left. So the anode is connected to the P region and the cathode is connected to the N region. The N minus region is basically same as N region, but the doping concentration is less. So that means the element which is introduced, which will provide the excess electrons, the concentration of that element in this region is less. And this is called the drift region. So this drift region, as I showed mentioned previously, by increasing the length of this drift region, the voltage withstand capability of the device will increase. So in order to have high breakdown voltage, we want to have a low doping concentration, and by increasing the width of this low doping concentration region, we will achieve higher breakdown voltage. Because when we reverse bias this diode, because the voltage withstand capability is for negative voltage for the diode. So whenever we withstand this reverse bias this diode, all of the voltage comes across this drift region because it has uh, lower concentration of carriers. So that is why by increasing the width of this drift region, the breakdown voltage will increase. So that means the length of the drift region and the breakdown voltage are directly proportional. So the answer to this problem is A, directly proportional. The breakdown voltage and the drift region are directly proportional. That means by increasing the drift region, we will increase the breakdown voltage. But again, as I mentioned previously, by this drift region, because it has low doping, it is also uh, a region of high resistivity. So that means for high breakdown voltages, that means for high drift region, if the drift region is longer, then the resistance, the on-state resistance of the device will also be higher. So that is there is a trade-off between the breakdown voltage and the resistance. So the eighth question is fast recovery diodes are used in which application? It can be small or low frequency, medium frequency, high frequency, and the reverse recovery time of these diode is what? What is it? Small? Is it high? Or so you can post your guesses in the chat. Okay, some are posting C. That means high frequency application and high reverse recovery time. So it is also important to, so you may know the answer, but if you are reading the question incorrectly, then you will choose the wrong option. So the question says that fast recovery diodes are used in which application? And the reverse recovery time of these diodes is what? So reverse recovery time and the application are actually uh, inversely related. So that will give you some hint. Okay, some people are saying D. So we can see, as I mentioned previously, in a normal diode, uh, during the turn-off process, the minority carriers, that is the holes in the N minus region, to remove those minority carriers, we require a negative current. And that negative current basically is the reverse recovery current, and that charge that we want to remove is the reverse recovery charge, or QRR. And that basically, depending on the rating of the device and uh, the structure of the device, it will take some time to take that charge out, and that is called the reverse recovery time. So this time, uh, the charge that is highlighted, the time it takes to remove this charge is called the reverse recovery time. And fast recovery diodes are made in such a way that this time is smaller. So they have recovery times of less than few microseconds, while standard diodes, it can be tens of microseconds or more than that even. So the fast recovery diode, basically the feature of this fast recovery diode is that the reverse recovery time is smaller. So what that allows us is to use this fast recovery diodes in converter applications with higher switching frequency. Because as I mentioned previously, because during the if the turn off process is long, very long, then this current basically it will lead to some losses because the voltage is also not zero. And the diode will be connected to some other device in the circuit. And this negative current will mean some positive current in that other device. And then there will be power losses in that other device. So if we can reduce this time, we can reduce the losses in the converter. And by reducing the losses in the converter, we can have higher switching frequencies because the switching frequency and the reverse recovery time are related such that if the reverse recovery time is large, then we will not be able to switch at very high frequencies because for every reverse recovery time, we will get some loss. And the switching frequency basically tells us how many times in a second we are having this reverse recovery loss. If we have a high switching frequency, that means we are having this reverse recovery loss uh, a high number of times. That means there will be a high loss and it will require a bigger heat sink as well as the temperature of the device will be very high. But if the reverse recovery time is less, then for the same loss, we can go to higher switching frequencies. And the advantage of going to higher switching frequencies, as I mentioned previously, by using low pass filters, we can filter out the high frequency components from our voltages. And if we have higher switching frequencies, then the filter components that we require will be smaller. We will require a lower value of inductance or a lower value of capacitance to filter out higher switching frequencies. So we want to go to higher switching frequencies, but we are limited by the switching losses in the devices. So that is why we make use of fast recovery diodes, because in the case of fast recovery diodes, the reverse recovery time is less. So that means we can go to higher switching frequencies. But again, nothing in power electronics comes free. If you are getting a low switching time, but in fast recovery diodes, we are not able to achieve high voltage ratings as the standard diodes. So there are pros and cons to both power electronic standard diodes as well as fast recovery diodes. So the answer to this question is that the fast recovery diodes are the fast recovery diodes are for high frequency application, and the reverse recovery time of these diodes is small. So I will share this the YouTube link as well as the PPT folder with the NPTEL team, and uh, they will probably share it with you. If they don't share it with you, then next week I will share the links to the whole YouTube channel as well as the drive folder with all the PPTs for the upcoming sessions as well. Okay. So the next question is the reverse blocking capability of a Schottky diode compared to power diode is number one, equal, extremely high, extremely low, or D, either extremely high or extremely low. So you can post your guesses now. Okay, so some are saying B, some are saying C. So again, now I'm showing the structure of the PN junction as well as the Schottky diode again. The PN junction, as I mentioned, it has a P semiconductor and an N semiconductor, and the N minus layer is in for power diodes, which is called the drift region. And because of this N minus region, we are able to get very high voltage ratings. But for Schottky diode, we have a metal and semiconductor junction. So we don't have a P portion, we have a metallic portion, and then we have an N semiconductor. And due to these different junction properties, the depletion region and the barrier height of Schottky diodes is much smaller than the power diodes. Because the depletion region and the barrier height, that will depend basically on how many the doping concentration of the P and N regions. And by increasing this N minus region, we can increase this depletion region. But in the case of Schottky diodes, this depletion region is very small because it has a different kind of a junction. It has a metal semiconductor junction. So that leads to a very low forward drop as well as low reverse blocking capability. So that means the Schottky diode will not be able to block as much voltage as the PN junction diode. So in the market, you can see that PN junction power diodes are available up to kilovolts of level. They can block kilovolts of voltages, but Schottky diodes are not able to block more than 100 or some hundreds or few hundreds of voltages. And this is also the reason why the uh, reverse leakage current of the Schottky diode is large because of the metal semiconductor junction. So the answer to this question is basically the reverse blocking capability of the Schottky diode is extremely low compared to a power diode. So the answer is C. Okay. Any questions about this? Okay. So now the 10th question, this is the last question. Which of the following devices has control turn on and control turn off characteristics? So you can control turn on and uncontrolled turn off. Okay. So this is relatively easy. So the diode, as we saw, it will turn on and turn off depending on the biasing voltage. So if the circuit is such that the voltage across the diode is positive and more than the barrier voltage or knee voltage, it will turn on. And if the voltage becomes negative or the current becomes negative, it will turn off. So nothing is in our control. Uh, we cannot. There is no other terminal where we can turn on the diode or turn it off. So it will entirely depend on the circuit and the circuit parameters. For the SCR, we will it has three terminals now. So and using the gate terminal, we can turn it on using by applying a gate current. So it will block both positive as well as the negative voltage, but it will only conduct in the positive direction from plus to minus, from anode to cathode. So it has a control turn on, but we cannot turn it off by providing a negative current. So that is a gate GTO. For an SCR, we can only turn it on by providing a gate current, but it will be turned off by the circuit. So if the voltage becomes zero or the current becomes negative, only then will the SCR turn off. So it has a control turn on using the gate current, but we cannot use the gate current to turn the SCR off. And the triac, as I showed previously, it is basically two SCRs connected in reverse anti-parallel. So one SCR is connected from plus to minus, I have shown here, and another SCR is connected from minus to plus. And both gates are connected, so that when we provide a gate current, uh, both of these sides can be turned on. So the current can flow in either direction, from positive to negative as well as from negative to positive. So this switch is basically a four-quadrant switch, because as we know, the SCR can block both positive as well as negative voltages. So the track will also block positive as well as negative voltage. And the track will also allow positive current and negative current. So it is a four-quadrant device. But the disadvantage of a triac is that we can turn it on by the gate current, but we cannot turn it off using a gate current. So it is a uncontrolled turn off. So now coming to the other options that were given, were the MOSFET and the IGBT. So again, the MOSFET and the IGBT, both of them can be turned on by applying a positive voltage. So that is a controlled turn on. And whenever the voltage crosses the threshold, in case of MOSFET, and it uh, crosses such that the IGBT comes out of saturation, the MOSFET and IGBT can be turned off. And by removing the gate voltage, we can turn them both off. So they have control turn on as well as control turn off. So that is very useful in power electronics, because we want to achieve a given pulse of our output voltage, and that can only be done by devices which have both control turn on as well as control turn off properties. So as we will see that MOSFETs and IGBTs are very popularly used for low voltage applications. Because as I mentioned previously, MOSFET is a majority carrier device. So we can use it for high switching frequencies, but with high voltage ratings, we will get uh, high resistance. So the conduction loss for high voltage ratings will be high. So that is why the application of MOSFETs, the silicon MOSFETs, is limited to less than 600 volts. But IGBTs are available for kilovolt applications as well, because they are minority carrier devices. But because of the minority carrier feature, the switching time of IGBTs is higher than MOSFETs. So we cannot use them for very high switching frequencies compared to the MOSFETs. So anyway, coming to the problem. So the problem I had asked, which has a control turn on and uncontrolled turn off. And out of these, SCR and triac, they both have controlled turn on and uncontrolled turn off. But since the D option also has MOSFET and triac, so the MOSFET does not have an uncontrolled turn off. So we cannot take MOSFET as the answer. So the only answer in this question is SCR. So these were the 10 questions that I had for this presentation. So in the next presentation, besides the summary of the weekly content, uh, I will also provide the solution of the assignment questions. So when is the deadline for the week one assignment? 9th. So is that before the next Monday? Okay. So I think then that will probably be beyond next Monday. So then we can solve it in the third Monday. So tomorrow's session will be taught by a different uh, PhD student, but the content will be same, because there are a lot of students enrolled in this course, and they don't all have uh, same availability. So we are providing you with different choices. So you can either come on Monday 6 to 8, or Tuesday 6 to 8, or 7 to 9. So these are different options, but the content will be the same. Uh, but in case you are able to come to both classes, then we can perhaps give different content. But that will be decided in future classes. For the tomorrow's class, they will be the same content. Okay, you're welcome. Any other question? Does anyone else have any question? Okay, but so there are actually a lot of students in the course, around 6,000 or 5,000 students enrolled in the course. So I don't know how we can give a poll to all the students. So right now there are only 53 students here. So even if you all agree to, you are available and you can come tomorrow, but we don't know uh, about the other students. And I don't think you have a WhatsApp group or something, but uh, so I think it will be best if we can just have the same content because there are a lot of students and some will be available on some days and others can be available on other days. So far, okay. Okay, we will see in the coming weeks. So the recording of this lecture will be uploaded on YouTube, and so I will consult the NPTEL coordinators whether you will be provided the link or whether then I can provide it in the next class. So you can also ask questions in the YouTube, or you can also ask questions in the course forum. So you just mentioned that this problem session of Monday, if you have any questions relating to specifically related to this session. Okay. So if anybody else does not have any question, we can then end today's session. Okay. Thank you all for joining. We'll see you next Monday. Okay, Onkar has a question. If the SCR is not control device, then how the SCR based rectifier works? So the SCR is controlled turn on, but the turn off cannot be controlled. So the SCR based rectifier basically works by we can control the average voltage by the initial pulse. So in an SCR based rectifier, we can turn the rectifier, the SCR on after some angle of the sine wave, but it will turn off when the voltage uh, goes to zero. So bipolar withstand capability. Okay, so that capability is in both HCR as well as GTO. Okay, so this question. So again, the SCR structure is shown here. The anode is connected to a P layer. After the P layer, we have an minus layer, which is a uh, lightly doped layer. And this P and N minus junction is called J1. Then after the N minus layer, we have another P layer, which is the junction from this N minus to P is J2, and from P to N is J3. And this P layer is connected to the gate, and the last N layer is connected to the uh, cathode. And the same is the case for GTO, just that we have more, uh, the structure is a bit divided differently, but the components are same from PN and anode, cathode, gate, and three junctions. So the point here is when we apply a positive voltage to anode across anode and cathode, that means the A is positive and K is negative. That in that case, if you see the junction J1 will be forward biased. So there will be a positive voltage across P and in this direction going from anode to cathode. The N minus will be connected to the negative voltage, so that will be the J1 junction will be forward biased. Similarly, J3 junction will also be forward biased because the this P is towards the anode and the N is towards the cathode. So J1 and J3 are forward biased. So forward bias will mean that it will not block that voltage. However, the J2 junction is reverse bias because this junction, the anode is, since the anode is positively, we are applying a positive voltage, so that positive voltage comes across the N minus, and the negative voltage of cathode comes across this P layer. So the J2 layer becomes reverse bias. So that means for positive voltage applied to the SCR, the J2 junction will block that positive voltage. Okay. So only when we provide a gate current, that gate current will provide us with charges that can basically overcome this reverse bias. So that means the SCR will block positive voltage and we can then turn it on by providing a gate current. So if we apply a negative voltage now, that means the K terminal, the cathode is positive compared to the anode. Then the J2 terminal, the J2 junction will be forward biased because the P is closer to the cathode and the N minus is closer to the anode. So this terminal from cathode to anode, the J2 junction will be forward biased. However, the J3 and J1 junctions will be reverse biased. So again, in the negative voltage case, two junctions will be reverse biased. So again, the SCR will be able to block negative voltage. And in case of negative voltage using the SCR, we cannot, the gate current will not be able to uh, basically overcome this reverse bias. So the SCR cannot be turned on in the negative direction. So it can block both positive as well as negative voltages, but it can only pass positive voltage from anode to cathode. So that is the uh, bipolar withstand capability. So that means it can withstand bipolar voltages. So whether the voltage is positive or negative, the SCR can block both voltages, but it can only pass positive current. So it will have a two quadrant. The first quadrant, which is positive voltage and positive current, and the second quadrant, which is negative voltage and positive current. So it will be a two quadrant device. And GTO is same. GTO allows us to turn, to allow us to have a control turn off, but in case of voltages and currents, it also has bipolar voltages and unipolar current. Okay, is that clear, Samullah? Okay, so if there are no more questions, then okay. If there are no more questions, then we can conclude the session. So thank you for your participation as well as your questions. Goodbye.